Welcome to Teolumen Insights, where we reveal the hidden forces that shape the way you live and show you how to use them to create real transformation and supercharge your health, mindset, and daily life. Here are your hosts, Emma Greenwood and Nathan Sinclaire.
Welcome back to Teolumen Insights. I'm Nathan Sinclaire.
And I'm Emma Greenwood.
And we are so excited to get into today's deep dive.
Definitely. It's going to be a fascinating one.
It is.
Exploring the Electro-Plasmic Universe.
Now, you might be joining us today because you've heard of this theory. Maybe you're prepping a presentation or you're just intrigued by this concept.
Right.
But either way, get ready because we're going to be diving into some seriously mind-bending concepts.
You're going to see plasma behaving in ways that you probably never thought possible.
Yeah. So let's start with the basics. What exactly is plasma?
Well, we hear about solids, liquids, and gases, right? Those are kind of the main states of matter that we think about.
Right, the classic three.
Yeah, but it's actually plasma that's the most common state of matter in the universe.
Really?
Yeah, and you'll see as we get deeper into this deep dive how influential it actually is.
So what is it?
So think of it this way. It's like a gas, but it's been supercharged.
Okay.
Some of the electrons in the atoms have been stripped away, leaving a mix of freely moving charged particles, and this gives plasma some really unique properties. It can conduct electricity.
Okay.
It reacts very strongly to magnetic fields, and it can even do cool things like forming those auroras that we see up at the poles.
Oh, wow.
Yeah.
So that's plasma doing that.
That's plasma.
I mean, where do we find plasma in the universe? Is it just floating around out there in space or?
Well, it's closer than you think.
Oh, really?
Yeah, even Earth has its own layers of plasma.
Okay.
The ionosphere and the thermosphere are prime examples. They're full of dynamic activity. And, one of the sources we're looking at today mentions something that's really kind of mind-boggling.
Oh, lay it on me.
NASA space shuttle missions, they've actually filmed these plasmas in the thermosphere, and they're massive, up to 1 kilometer in size.
Wow.
And they exhibit what, some people might call lifelike behavior.
Wait a minute. Did you say lifelike?
Yeah.
Kilometer-sized plasmas? That sounds like science fiction. What do you mean by lifelike?
Well, they've been observed, moving in formations, changing direction, even interacting with satellites.
Wow.
It really makes you wonder if there could be other forms of life out there that are maybe based on plasma rather than, the biological molecules we're used to.
That's crazy.
Right. It really challenges our definition of what life could be.
Wow. Okay, so we've got plasma right here in our backyard.
Yeah.
But this electroplasmic universe theory, that takes things to a whole other level, right?
It does.
What's that all about?
Basically, it suggests that electromagnetic forces, they play a much bigger role in the universe than we typically give them credit for.
What?
Most of astrophysics focuses on gravity as being the big guy shaping galaxies and holding stars together. But this theory is saying, hey, electromagnetism, it's got a much more active role.
Okay.
It's influencing everything from the formation of stars to the structure of galaxies.
But that's not just gravity holding everything together.
Right.
These forces are almost shaping the universe.
Exactly.
Okay, so how does that all fit into this electroplasmic universe theory? Where do these electromagnetic forces come in on such a huge scale?
That's where we get into things like Birkeland currents.
Birkeland currents.
Yeah, and they are massive flowing currents of plasma.
So, are we talking humongous intergalactic power lines, crackling with energy?
You're kind of getting the idea.
Okay.
These currents can stretch for light years, carrying huge amounts of energy and shaping the cosmos in ways that we're just beginning to understand.
It's hard to even imagine.
And what's really interesting is the electricuniverse.txt source that we're looking at.
Yeah.
It suggests that ancient people might have actually seen these currents in the sky. They might have looked up and seen colossal lightning bolts or gigantic cyclones.
Wow.
And this might have inspired some of their myths and even the deities that they worship.
So the ancient gods of thunder and storms could have been inspired by actual cosmic events.
Yeah, it's possible.
That's incredible.
It really is. It paints this picture of ancient people looking up at the night sky and seeing these awesome displays of power.
Right.
Even without, the fancy telescopes we have today.
Right. So how do these Birkeland currents tie into something like star formation?
Well, that's where we get into another really interesting concept from the Electro-Plasmic Universe theory.
Oh, okay. What is it?
And that's the idea of electric stars.
Electric stars. So are you saying that stars are like giant power plants powered by electricity instead of nuclear fusion, like in science fiction?
Yeah, it's a bold claim.
It is bold.
But the electric star model, it suggests that stars are essentially giant balls of plasma, and they're powered by these galactic-scale electric currents.
Okay, and these are the Birkeland currents we were talking about. So instead of being fueled by internal nuclear reactions, stars are more like these cosmic light bulbs plugged into a giant intergalactic power grid.
It's a pretty radical concept.
It is.
And while it definitely challenges, the traditional view of stellar evolution, it does show the power of plasma and electromagnetism in shaping the universe.
And it opens up a whole new way of thinking about how stars are born, how they evolve, how they die.
Exactly.
Okay, so this is really making me question everything I thought I knew about the universe.
Yeah.
But before we get too lost in the cosmos, let's bring it back down to Earth for a second.
Yeah.
You mentioned that this electro-plasmic universe theory, it challenges some pretty fundamental assumptions in astrophysics.
It does.
Can you talk about that a little bit?
One of the sources we're looking at today, it's a 14CO37377V1.pdf.
Yeah.
It actually dives into all these tests of Einstein's theory of gravity.
Right, the big one.
Yeah, and while it acknowledges that Einstein's theory is really robust, it's been confirmed by so many observations, it does point out some areas that, maybe could be investigated further.
So it's not about discounting Einstein's work.
No, not at all.
But just kind of pushing the boundaries, maybe looking at things from a different angle.
Exactly. Science is about questioning, about testing, about refining our understanding.
Right.
And this electro-plasmic universe theory, even if some of its ideas end up, being disproven, it forces us to look at what we think we know.
Absolutely.
And to consider new possibilities.
That's what makes it so cool. It's all about exploration, right?
Exactly.
So speaking of exploration, let's get into some of the specific phenomena that this electro-plasmic universe theory uses to explain the universe.
Okay.
One thing I keep hearing about are double layers.
Yeah.
What are those?
Double layers, they're fascinating.
Okay.
Imagine a region within a plasma where there's this sudden jump in electrical potential. It's like an invisible wall where all this electrical energy is concentrated. And these double layers, they can accelerate particles to crazy speeds.
Oh, wow.
Generate really intense electric fields, and even give rise to some of these really strange phenomena that we've been discussing.
So they're like cosmic particle accelerators.
Yeah, you could think of them that way.
Could they explain those movements, those lifelike movements we saw in those massive plasmas in the thermosphere?
It's certainly a possibility.
Wow. Okay.
Yeah, double layers are found everywhere in the universe,
Right.
from the sun's atmosphere to distant nebulae.
Wow.
They're a prime example of how electromagnetism can create some really dramatic and unexpected effects in plasma.
Okay, so dramatic effects.
Yeah.
What about magnetic fields? How do they fit into this whole electroplasmic universe?
Oh, magnetic fields, they're huge in this.
Okay.
We learn about them in school. It's all about attracting or repelling, like with magnets.
Right.
But in the electroplasmic universe, magnetic fields are like this invisible scaffolding.
Okay.
They guide the flow of plasma. They influence the formation of everything from stars to galaxies.
Oh, wow.
They're like the architects of cosmic order, shaping the universe on a grand scale.
So it's almost like the universe is playing this giant game of cosmic twister with plasma and magnetic fields.
That's a fun way to think about it.
Yeah. So what happens when a plasma gets caught in one of these Z-pinches?
Things get really hot
Okay.
and very bright.
Okay.
Z-pinches can generate insanely high temperatures and just release tons of energy.
Wow.
Some people who support the electroplasmic universe theory even think that Z-pinches might be responsible for some of the most energetic events in the universe.
Oh, well, like what?
Like supernovae,
Uh-huh.
or even the jets that come out of active galactic nuclei.
Oh, wow. So we could be talking about explaining some of the most powerful events in the universe using plasma physics. That's a pretty big departure from traditional explanations.
It really is.
Hey, I got to say, some of these terms I've been reading about, they're making my head spin a little bit.
Yeah, it can be a lot.
Non-thermal continuum,
Yeah.
phase velocity, helicon waves.
Yeah, it's a whole new language.
It is. Can you break some of those down for us?
Sure, let's start with non-thermal continuum. So Imagine you're looking at a star through a prism, right?
Okay.
And instead of seeing like distinct colors of light, you see this continuous spectrum, like a rainbow that's all blended together.
Yeah.
That's kind of what we mean by non-thermal continuum in plasma. It emits radiation across a bunch of different frequencies, and that tells us a lot about, the plasma's temperature, its density, other properties.
So we're taking the temperature of the plasma
Exactly.
by looking at the light it emits.
Yeah.
Okay, what about phase velocity?
So think about watching waves, like rippling across a pond.
Uh-huh.
The speed at which those ripples are traveling, that's the phase velocity. And in plasma physics, we're talking about waves of energy traveling through the plasma, and the phase velocity tells us how fast those waves are moving.
Okay, that makes sense.
Yeah.
What about helicon waves and Alfvén waves? Those sound like something out of Star Trek.
They do, right.
Yeah.
But they're actually pretty common in the universe.
Okay.
Helicon waves, those are low-frequency waves, and they're really important in laboratory plasmas where we use them to heat and confine the plasma.
Oh, okay.
Kind of like stirring a cosmic pot.
I like that, yeah.
Yeah, Alfvén waves, on the other hand, they're like magnetic ripples traveling through the plasma.
Okay.
So think of it like, those waves you create when you shake a rope up and down.
Uh-huh.
And they're thought to be really important in transporting energy from the sun's interior to its outer atmosphere.
Wow.
Which is, as you know, millions of degrees hotter than its surface.
It is very hot, yeah. So we have all these different waves traveling through this plasma, carrying energy, information across these vast cosmic distances. It's amazing how much is going on in something that sounds as simple as ionized gas.
It really is.
And speaking of things that sound simple, I keep seeing this term sheath. What is that all about?
It's not as scary as it sounds.
Okay, good.
A sheath is just a boundary layer that forms between a plasma and a solid surface.
Okay.
So think of it like a buffer zone where the plasma and the surface can interact.
So it's like a cosmic DMZ.
Exactly.
Okay, so what's the big deal about these sheaths? Why are they so important?
Well, they're super important in plasma processing because they control how ions from the plasma actually hit the surface.
Oh, okay.
And this is critical in things like semiconductor manufacturing where, you need that very precise control
Right.
to create those tiny features on microchips.
Yeah, it's amazing how something that sounds so simple can have such a huge impact on technology and the things that we use every day.
Exactly.
So before we wrap up this part of our deep dive, I want to touch on a few more technical terms I found interesting.
Okay, sure.
Things like radio frequency sheaths, quasi-neutrality, electronegativity, and even dark and dusty plasmas. What are all those?
All right, well, those are all specific but important aspects of plasma physics that kind of build our understanding of this really dynamic field, like radio frequency sheaths. Those are sheaths that form in plasmas that are excited by radio frequency waves,
Okay.
which are commonly used in a lot of industrial applications.
So it's like giving the plasma a little jolt of energy to get it going.
Exactly. And then you have quasi-neutrality, which is a super fundamental principle
Okay.
that essentially says on large scales, plasmas tend to be electrically neutral.
Okay.
So the positive and negative charges within the plasma, they balance each other out.
Like a cosmic balancing act.
Yeah, exactly.
Okay.
And then there's electronegativity, which is the tendency of some plasma species to attract electrons and become negatively charged. This can really affect how a plasma behaves, influencing things like its stability and how well it conducts electricity.
Okay, so some particles in the plasma are playing this cosmic game of electron capture.
Yeah, that's a great way to put it.
Okay, and lastly, what about dark and dusty plasmas?
Okay, so dark plasmas, they're simply plasmas that don't emit much light.
So they're hard to see.
Yeah, they're kind of like the ninjas of the plasma world,
Okay.
lurking in the shadows. And then you have dusty plasmas, which are plasmas that contain dust particles.
Dozen particles.
Yeah, and they can really impact the plasma's properties.
Interesting.
For example, the dust particles, they can be like nucleation sites for new particles to form.
Oh, okay.
So they can really influence the chemical processes going on within the plasma.
It's incredible how much complexity there is in something as seemingly simple as ionized gas.
It is, and we've only just scratched the surface.
I know.
There's so much more to discover in this amazing realm of plasma physics and cosmology.
There is, but for now we'll leave you with a question to ponder. If electromagnetism is as influential as this electro-plasmic universe theory suggests,
Yeah.
Could it be responsible for shaping not just stars and galaxies, but the very structure of the universe itself?
Interesting question.
Join us for part 2 as we dive even deeper into the mysteries of the electroplasmic universe and explore this concept of cosmic currents in more detail.
And until then, keep those cosmic questions coming.
Absolutely.
Welcome back to Teolumen Insights. I'm curious, out of everything we talked about last time, what really stuck with you?
I have to say, those kilometer-sized plasmas in the thermosphere that seem to be exhibiting those lifelike behaviors, that was pretty wild.
It's a fascinating idea, right? It makes you wonder what else we might be missing, what other secrets are out there.
Absolutely, yeah. So what are we diving into today?
Well, I came across this term space charge while I was doing some reading, and it really piqued my interest.
Space charge, yeah, that does sound pretty intriguing. What is that exactly?
It's basically a key concept in understanding how electric fields behave within a plasma.
Okay.
So picture a region in space where you've got this imbalance of positive and negative charges.
Okay.
And this creates a net electric charge, which we call space charge.
Okay, so it's like an invisible force field.
Yeah, you could think of it that way, and it can influence how those charged particles within the plasma move around.
So space charge is like the invisible hand guiding the plasma's movements.
Yeah, that's a good analogy.
So how does space charge actually affect how the plasma behaves?
Well, for starters, it helps shape those electric fields within the plasma.
Okay.
And then those electric fields, they can accelerate particles, generate waves, even contribute to the formation of those double layers we were talking about.
Oh, right. Those zones where there's a sudden jump in electrical potential.
Exactly. Space charge can play a big part in making those happen.
I see. So it's all kind of connected then. Space charge affects electric fields affect double layers then accelerate particles, and then boom, we get all these cool phenomena.
Exactly.
Like a chain reaction, but on a cosmic level.
That's a great way to put it. And that's what's so cool about this electro-plasmic universe theory. It shows how everything's connected in the cosmos, you know?
Right, from the smallest particles to the largest structures.
Yeah, exactly. And speaking of connections, let's go back to those Birkeland currents for a minute.
Okay.
You know, we were talking about them being like these giant intergalactic power lines stretching across vast distances.
Yeah, that was mind-blowing.
But how do they fit into this bigger picture of the electroplasmic universe? You know, we've been talking about plasma and electromagnetic forces on a smaller scale, like within stars or galaxies.
Right, yeah.
But how does it all work on a universal scale? Does this theory explain how the universe is structured on that massive level?
That's a great question. I mean, we know galaxies aren't just randomly scattered throughout space, right?
Right.
They're clustered together in these filaments and voids, almost like a giant cosmic web.
Exactly. And the electroplasmic universe theory, it suggests that this web-like structure might not just be from gravity.
Oh, okay.
It could be shaped by these even larger scale flows of plasma
Oh.
driven by, you guessed it, Birkeland currents.
So these Birkeland currents, these massive filaments of plasma, they could actually be interconnected on a much, much grander scale, almost like a circulatory system running through the entire universe.
Exactly.
That's incredible.
Imagine these currents flowing through the cosmos, connecting galaxies and clusters of galaxies like beads on a string.
It's an amazing image.
It is a universe that's alive with these electric currents, shaping the very fabric of space and time.
That's incredible to think about. But if these currents are actually out there, shouldn't we be able to see them, detect them somehow?
Well, you're right. It's a challenge to directly observe these currents.
Right.
But there are some observations that really fit with what the electroplasmic universe theory predicts. Like what?
Well, for example, the way galaxies are aligned along those filamentary structures,
Okay.
and the fact that we see magnetic fields in the space between galaxies, these things are really hard to explain using just gravity.
Yeah, that makes sense.
But they fit perfectly in a universe that's filled with electric currents.
So it's like we're putting together a giant puzzle, and we have these pieces that don't quite fit the traditional gravity-based model.
Right.
But then along comes the electroplasmic universe theory, and suddenly it's like, oh, those pieces, they fit here, and we can finally see the whole picture.
That's a great way to put it. And remember, science is all about constantly discovering and refining our understanding.
Right.
We're always gathering new data, challenging old theories, exploring new possibilities.
Absolutely. And the electroplasmic universe theory, even if some of its ideas turn out to be wrong, it gets us thinking outside the box.
Exactly.
And that's what's so exciting about it.
It is.
So let's go back to something we touched on earlier.
Those Birkeland currents and their powerful magnetic fields.
Mm-hmm.
I'm curious, how do those magnetic fields interact with the plasma itself? Do they do anything interesting?
Oh, they definitely do.
Okay.
Remember phase velocity, the speed at which waves travel through plasma?
Yeah.
Well, when you add magnetic fields into the mix, things get even more wild.
Okay.
Because those magnetic fields can actually influence the phase velocity of the waves.
Right, yeah.
It's like this cosmic dance between the plasma and the magnetic fields.
So it's like the magnetic fields are choreographing the movements of the plasma, like guiding the flow of energy throughout the universe.
That's a beautiful way to put it, and this interplay can lead to some really fascinating things happening.
Oh, like what?
Well, one example is something called magnetic mirrors.
Magnetic mirrors.
Yeah, imagine a region where those magnetic field lines are coming together, like a bottleneck.
Okay, yeah.
And then charged particles, like the ones in plasma, they get trapped in these regions, bouncing back and forth between the field lines.
So it's like a cosmic pinball machine.
Exactly.
Do magnetic mirrors play a role in forming stars or planets?
It's definitely possible you find them all over the universe.
Wow.
From the Earth's magnetosphere to distant nebulae, and they can have a huge impact on how plasma behaves.
It's amazing to think about all these forces at play, shaping the universe in these grand and complex ways.
It is, and it's humbling, to realize that we're just tiny specks in this vast and mysterious cosmos.
It is. It's almost overwhelming to think about, but at the same time, it's so exciting.
Absolutely. That's what makes exploring these ideas so captivating.
Totally agree. So we've been talking about these grand cosmic scales.
Right.
But are there any practical uses for these concepts, here on Earth? Does understanding this electroplasmic universe actually affect our everyday lives?
That's a great question, and the answer is a resounding yes.
Really?
Even though the electroplasmic universe theory challenges some of the big ideas in astrophysics, its principles are actually being used in lots of different technologies right here on Earth.
Oh, wow. Like what?
Well, one really promising application is in fusion energy.
Fusion energy, like the power source of the stars, that fusion energy.
That's the one.
Wow.
And as we've learned, plasma is a big part of how fusion reactions work.
Right.
So figuring out how to control and use plasma with electromagnetic fields is going to be crucial if we want to achieve controlled fusion.
And if we can figure that out.
It could change how we get our energy forever, making it cleaner and more sustainable.
That's incredible. So studying the cosmos, these things that seem so abstract like plasma and electromagnetism, they could actually help us solve some of the biggest challenges facing humanity.
Exactly, and that's just one example.
Wow.
Plasma physics principles are being used in all sorts of fields, like materials science, making semiconductors, even medicine.
It's amazing how much potential there is in something that, again, sounds so simple, ionized gas.
It is.
So I think it's time to wrap up this part of our deep dive. We've covered a lot of ground, from space charge to the idea that cosmic currents might be shaping the structure of the universe.
Right, and we even touched on how these ideas could be used here on Earth.
Yeah, and there's still so much more to explore. But for now, we'll leave you with another question to ponder. If the universe is really this vast network of plasma and electromagnetic forces, like the Electro-Plasmic Universe theory suggests, what does that tell us about our place in the cosmos?
Good one.
Join us in part 3 as we dig even deeper into these big questions and explore what the electroplasmic universe means for how we see ourselves and our place in all of this.
And until then, keep those cosmic questions coming.
Welcome back to Teolumen Insights. We've been on quite a journey through the electroplasmic universe.
We have, from those strange plasmas in Earth's thermosphere to those massive cosmic currents that could be shaping, well, everything.
Yeah, it's been a lot to take in.
It has. So as we wrap up our deep dive, I'm curious, what's been the most surprising thing you've learned so far?
For me, it's definitely the sheer scale of it all. The idea that these invisible forces, electromagnetism, these currents and fields could be responsible for the structure of the entire universe, that's just mind-blowing.
I know, it really makes you feel small, doesn't it?
It does, but also kind of connected. Like we're part of something much bigger than ourselves.
Exactly. It changes how you see yourself in the cosmos, doesn't it?
It really does. Instead of being just observers, we're like participants in this incredible cosmic dance of plasma and energy.
I love that, a cosmic dance.
But if everything is really connected like this, it makes you wonder about the nature of reality itself. If the universe is basically this giant electrical circuit, does that change how we understand how it all began?
It's a big question, and one that's had scientists and philosophers debating for, well, forever.
So what does the electroplasmic universe theory say about the beginning of the universe? Does it challenge the Big Bang theory?
It does offer a different perspective. The Big Bang says the universe started from a single point and has been expanding ever since, right?
Right.
But the Electro-Plasmic Universe suggests something totally different. It says the universe is infinite, both in space and time.
Okay.
So there wasn't a single starting point.
So instead of a universe that's expanding from a tiny point, it's a universe that's always been here, just this endless sea of energy and matter.
That's the basic idea, yeah. And in this infinite universe, matter is constantly being created and destroyed all through the interplay of electromagnetic forces.
So it's like a constantly evolving universe, not one that started with a bang, but one that's always been in motion.
Yeah, it's a pretty radical concept, I know.
It is. It makes you wonder if the universe is infinite and eternal, was there ever really a beginning?
That's a question that dives into philosophy, and one that this theory doesn't necessarily answer. It just kind of shifts the focus from a single moment of creation to this ongoing process of creation and destruction, a dance that's been happening forever.
It's hard to wrap your head around.
I know, but it's definitely fascinating to think about.
It is. So we've been talking a lot about electromagnetism, but what about the other fundamental forces of the universe, like gravity? How does that fit into this theory?
It's a good question, and one that's at the heart of a lot of scientific research.
Okay.
The Electro-Plasmic Universe emphasizes electromagnetism, sure, but it doesn't say the other forces aren't important.
Right.
It's more like maybe these forces are all connected in ways we don't fully understand yet.
So instead of seeing them as separate forces, maybe they're all just different expressions of one big unified force.
That's a possibility that a lot of physicists are exploring, and it's an idea that goes way back, like Einstein was searching for a unified field theory, and today we have string theory.
And it's all driven by this desire to understand how the universe works.
Right.
We want to know what makes it tick, what are the fundamental laws that govern everything.
And we've come a long way in our exploration of the electroplasmic universe, but we've only just scratched the surface.
That's the exciting part. There's still so much more to learn, so many mysteries to unravel.
It's a journey. And the electroplasmic universe gives us a new way to look at those mysteries, a new lens through which to see the cosmos.
And maybe, as we continue down this path, we'll not only learn more about the universe, but also about ourselves, our place in it, and the nature of reality itself.
It's an incredible thought, isn't it?
It is. Thank you for joining us on this journey through the electroplasmic universe. We hope you've enjoyed it.
We hope it's made you curious, made you want to explore these ideas even further.
The universe is full of wonders. Keep looking up, keep asking questions, and keep exploring.
And thanks for listening to Teolumen Insights.